Hello. I have a two-dimensional collision example for you today. This is coming directly out of your text. In this problem, we have two protons that are colliding with each other. The first proton, which we're going to call M1 for a little bit, initially starts with a velocity of 3.5 times 10 to the fifth meters per second, which is really fast. And it's going to collide with another proton, which we're going to call M2, again, just for a minute here, and we're going to see how these are actually going to cancel out. And when it does that, it's not going to do it linearly so that their centers of mass are hitting in line with each other. Instead, this one's going to glance off of it. And that's what's going to cause these two masses to separate and bounce off at these angles that we're going to call theta and psi down here. All right. So our goal in this problem is to calculate a few things. We want to calculate the speeds, v1 and v2, that they bounce off with. And we are also given in this problem that theta is equal to 37 degrees. So we also want to calculate the angle psi that mass 2 bounces off at. So we're going to break this down into three videos. In the first video, we're going to write the equations for the conservation of total linear momentum before and after the collision. In the second video, we're going to combine those two equations using some trig identities. And in the third video, we are going to finish that all off with the conservation of total kinetic energy, because this happens to also be an elastic collision. So let's get started on the first part. Before the collision, we have the two objects, and they are pretty boring. M1 is traveling to the right, and it has a speed. But that is an entirely horizontal velocity. So that means we have a horizontal momentum. But in the after collision, we have both horizontal momentum because there's some left to right action here, but we also have some vertical momentum because there's some up and down action here. So when we write these, we're going to separate them into vertical and horizontal. And that's kind of our first principle, is that when you have a two-dimensional collision, total linear momentum is conserved in all dimensions. So the vertical total linear momentum is conserved and the horizontal total linear momentum is conserved. So let's start with vertical because it's the easier to write of the two. And for our vertical direction here, initially, there is no up or down velocity. So there's no momentum to start. All right. Now, after the fact, we're going to have the momentum in the y direction for mass 1 here, and the momentum in the y direction for mass 2. All right, now, because these are hitting at angles, then we have components of these velocities that we're actually going to use. So I'm going to find the components of v1, all right? So the final velocity there in the y direction for our first mass is going to be our final velocity. And because this is the vertical side, we're going to use sine times the sine of theta. All right, and then down here for V2, we're going to have our final velocity times the sine of this angle psi. All right, and those are our two components that we're going to use as our velocities um, in this vertical direction for our momentum. So I have m1 times v1y, but we're just going to go straight for v1 times the sine of theta. And then that's going to be combined with the momentum for my mass 2. So that's going to be mass 2 times v2 sine psi. And we can kind of think of this a couple different ways, but because mass 2 is kind of pointed in the downward direction, we could use a little negative here and say that we're really subtracting these two momenta, and that's what's causing us to get zero total momentum. And then I'm going to rearrange this a little bit. So what I end up with is that m1 v1 sine theta is equal to m2 v2 sine psi. Now, because these are both protons, they have the exact same mass, and that means M1 and M2 are equal. They're the same value, and so we can just divide them out on both sides. We also know that they're not zero, and that's because you're not allowed to divide by zero. So I end up with this expression, V1 sine theta equals V2 sine psi for my vertical momentum. This is a pretty simple equation. I'm going to rewrite this up above here and save it for later. So for the horizontal, this is going to be our conservation of linear momentum equation. All right, so let's attack the horizontal now. This one's going to be a little bit longer because we do have an initial momentum. So in the horizontal direction, initially, our total momentum, right, should equal our total momentum after the collision. And these are in the x direction because they're horizontal. Well, we have m1, and it's traveling with an initial velocity in that horizontal direction, v1 initial, all right? And that's going to be equal to the total momentum after in the horizontal direction. And we haven't written those expressions, but using the same kind of idea before, v1x would be v1 cosine of theta, and then v2x would be v2 times the cosine of psi, all right? And we're going to use that a lot of the same way that we did before. So I have m1 times v1 cosine theta plus m2 v2 cosine psi. And again, these masses are all the same, and because they're on all of our terms, they're going to drop out. Okay, and we get an expression for v1 initial is v1 cosine theta plus v2 cosine psi. And so using this equation together with the, whoops, that was vertical, wasn't it? Together with the vertical equation that we got before, we're well on our way to calculating all of these values. Now there's a lot that we don't know, and if you look at these two equations, there's a few that are unknown. V1 is unknown and V2 is unknown, and that shows up in both of these equations. But not only that, psi is also unknown. And so we have three unknowns and only two equations, and we know that that's kind of a no-no in math. So we're going to have to come up with a solution, and that's what we're going to do in part 2.